Yeah, ours is yeah, we don't have enough people for that. You guys probably do. It's only like 5 of them. We built it. Yeah.
Okay, let's get started. Happy Friday, everybody. We got quite a bit of housekeeping to take care of before we get back to lecture. So let's talk about today and next week. Today, more specifically this afternoon, the Vermont Complex Systems Center is holding kind of like an open house, or otherwise known as a flash mob research event. These are informal events we hold every once in a while where we invite people to come in and learn a little bit about the research we're doing in the Complex Systems Center. So if you've wondered about what your professor does when he or she is not teaching, you can come and hear a little bit about it. We start at noon. It goes till 4. You can come for as long or as short a period as you like. It's going to be over in Farrell Hall, which is on the Trinity campus. And here's the schedule. So no PowerPoint allowed this afternoon. At any one time, 3 faculty will be working at 3 different whiteboards in the building, and you can sort of circulate and learn a little bit about what everyone works on. Professor Almasalki is in electrical engineering. He does research in smart grid. Professor Scarpino is a mathematician and does work on the spread of disease, and these days particularly the Zika virus. I will be talking about evolutionary robotics. At 1 o'clock, Professor Hines, also in the EE department, will be talking about smart grid. Dr. Spector is a heart surgeon over in the hospital. He's an actual practicing surgeon, but he also does some research on the side using evolutionary computation to guide surgery for atrial fibrillation, so hearts that don't beat in a rhythmic manner. Very exciting research. Professor Dodds in the math department will talk about all things Twitter. 2 o'clock, Dr. Bagro in the math department will talk about data science and network science. Professor Garavan does brain imaging studies, again over in the hospital. Can you predict somebody's behavior by scanning their brains? The answer is, in some cases, yes. Very interesting research again. Dr. Tivnan is going to talk about computational finance. Mr. Abely will be joining us, who's done a lot of work in developing equipment, medical equipment. We'll be talking about Fitbits for the brain. Dr. Danforth, Professor Danforth in math, also will talk about Twitter and more generally socio-technical sensing. And Professor Epstein here in the computer science department will be talking about one of the latest and greatest machine learning algorithms out there, deep learning, applied to audio data. So we've tried to pack in 4 hours here a lot of interesting research. They will be trying to talk about their research for a general audience, so no PowerPoint, as little equations as possible. Should be really exciting. You're all welcome. And most importantly, you can see the bottom item there, free food. So if you have some time in your schedule this afternoon, come and join us. Okay, so that's this afternoon. Looking ahead, let's see, where are we here? We are Friday, September 16th. We're going to finish lecture 4 today on philosophy, design, and process, and we may have time to start in on lecture 5, but I'm going to spend most of today talking about deliverable 4. So most of you hopefully are working your way through deliverable 3, which, as I told you, is a monster. It's the longest deliverable of all 10. How many people at least have started in on deliverable 3? Okay, excellent. Who is about halfway through or more? That's good. Okay. Anybody still struggling with installation issues? No hands. All right. Fantastic. I think everyone who is still with us has managed to get Matplotlib, Leap Motion, and what am I missing? There's a third, sorry? NumPy, right? So far you've worked your way through 3 Python packages. In Deliverable 4, which I'm going to talk about today, I'm going to introduce the 4th and final package that you'll be using in this class, scikit-learn, which is a machine learning package for Python. So Deliverable 3 is due next Monday morning. I won't be here on Monday, which is when I would usually talk about the next deliverable, so we're going to talk about it today. Deliverable 4 is due the following Monday, the 26th. So far, so good? Okay. Next week, let's talk about next week. Monday and Wednesday, Jeff Springer will be here, the CEO of Zemo Corporation, and he's going to be showing you a little bit of the alpha version of their educational robotics software. Later this afternoon, I'll put up an announcement on Blackboard where you can go and actually download it. If you can try and download it and install it on your machine before class on Monday, that would be great. If you can't, that's fine. This is sort of optional. Okay, so Jeff is going to walk you through on Monday how to use the software, and then on Wednesday, he's going to do some user testing with you. So last class, we started talking exactly about user testing. What is one of the big challenges about user testing in HCI?
Acceptability.
Acceptability? How so? Why is it challenging?
Because you can't test it before it's deployed.
You can't test it before it's deployed, right? My cell phone beeps when its battery is low right when I'm falling asleep every night. Not very acceptable.
Did you fix that?
Not yet. Okay. I need some IT help. Please, someone come see me in my office hours. We'll get it figured out. Okay. One of the biggest overall challenges of user testing is measurement, right? So your user sits down, they use your software for half an hour, and they fill out a survey, and they say, yeah, it was fun. Or I didn't really like it that much. Where do you go from there, right? How do we actually sharpen our measurements and actually get some quantitative data to figure out what aspects of the software we need to improve? You're going to get to be on the receiving end of this next Monday and Wednesday to get some firsthand experience. I will not be here on Friday, so we are not going to have class on Friday. Don't come to class next Friday. However, I do have video lectures from last year, so I will make V9 here live before Friday, so you don't have to come to class, but you still have to watch the video lecture, and there will be a quiz Friday night on material drawn from that video lecture. So you get to watch me on YouTube rather than in person. Sound good? And the deal is if you let me do this, I will bring you back something from Scotland. There's been a request for haggis and scotch, neither of which I think I can bring, but I will bring you something good from Scotland as a bribe. Monday and Wednesday, there will be no quiz, but again, Deliverable 3 will be due on Monday, Deliverable 4 the Monday after that. And then I will be back here with goodies on Monday the 26th. All right, we all good on what's happening today and next week? Good? Okay, so let's talk about the deliverables. Anybody have any questions about Deliverable 3? So far, so good? Okay, so let's talk about Deliverable 4. And in order to talk about Deliverable 4, I want to just take a step back and sort of recap where we've been and where we're going, if I can. Let's see here. If I can. Okay, so where are we and where we're going? As you remember, we started with the Leap Motion device right out of the box, where Leap Motion has 2 infrared cameras, and it's collecting pixel intensities in real time. And then the Leap Motion software under the box is taking these pixel intensities and turning them into 3D coordinates. So we're going from our 2 infrared cameras to 3D coordinates, which in deliverables 1 and 2, you've been turning into a real-time visualization in Matplotlib, right? So we've gone from pixels to coordinates to real-time visualization. In deliverable 3, you're turning those 3D coordinates, you're packaging them into a NumPy matrix, and in this case we're working with 3D matrices. What's the shape of this matrix? What are the 3 dimensions?
5 by 4 by 6.
5 rows for each of the 5 fingers, 4 columns for each of the 4 bones in each of the 5 fingers, and 6 stacks, which correspond to the base and tip of each bone in each finger, right? So we're packaging stuff up all the way from pixel intensities to, at least for one static frame, one 3D NumPy matrix. So in 1 and 2, we introduced the matplotlib library. We introduced the Leap SDK in 1 and 2. Deliverable 3 here, you're getting used to NumPy. So numerical manipulation in Python. In 4 and 5, deliverables 4 and 5, you're now going to be taking your 3-dimensional matrix and transforming this into a single integer, which is the computer's guess about which of the 10 digits from 0 to 9 the user is attempting to sign, right? So you've got pixel intensity, coordinates, a 3D matrix. Is this 0, 5, 9? Is it none of the 10? What actually is contained inside this matrix? So in deliverables 4 and 5 now, you're going to be adding in a machine learning algorithm, and that machine learning algorithm is going to take as input a bunch of these and learn how to then take a new one of these and output a prediction. All machine learning algorithms more or less have that one trait in common. Take a whole bunch of data and make a prediction about a pattern that is hidden somewhere in that data. Okay. In order to do this machine learning, we're going to use the 4th and final Python library that we'll talk about in this class, which has the very cryptic name of scikit-learn. Okay. So how exactly is this going to work? In deliverable 4, the first thing you're going to do is set aside your Leap Motion device for a little while. We don't need this anymore. We're going to set aside our Leap Motion device, and we're going to focus in deliverable 4 just on using scikit-learn with some synthetic data, so data that's already been prepared for you. And we're going to make sure that our machine learning algorithm is correctly making predictions. Once you've got that working in deliverable 4, in deliverable 5, the only thing you're going to do is remove the synthetic data and instead provide real data that's coming from your own hand. So far, so good? Okay, so what machine learning algorithm are we actually going to be working with? We are going to be using one of the very simplest machine learning algorithms out there called k-nearest neighbor, or KNN. The reading for today is simply the Wikipedia entry for the k-nearest neighbor algorithm that you can see here. And I'm going to just walk you through the intuition behind this algorithm. Has anybody worked with k-nearest neighbors before? No? Okay. Let's start with the data first, then we'll talk about the machine learning algorithm. There's a very famous data set out there called the IRIS data set. This was collected almost 100 years ago by someone in the Gaspé Peninsula going through a field and picking flowers. They were picking particular flowers, iris flowers. And for every flower that they picked, they measured 4 features of that flower. We're not going to worry about what those actual features were, but they had to do with the length of the petal and the width of the petal and so on and so forth. You can go and read about it. So for each flower that they picked, they wrote down 4 measurements, these 4 features. They then, it was a botanist who did the picking. This person knew when they picked a flower, which species did this particular iris belong to. So iris is the genus. Which species was it? Turns out that in this particular field there were 3 species of iris. Again, we're not going to worry what those specific species are. We're just going to worry about the class. So 3 species, there are 3 possible classes that any picked flower can belong to. Okay. So they picked the first flower, they recorded the first 4 features, and it turns out that that particular flower belonged to the first of the 3 species. This is computer science, so we always start counting from 0. Okay. They picked a second flower, they measured those 4 features, and they also determined, in this case, that that flower belonged to the 3rd species, and so on and so forth. Okay. They picked a total of 150 flowers, and that's what the iris data set is. And when you use scikit-learn, one of the first things you're going to do in Deliverable 4 is actually pull out that data set. Okay, so on line 4A here, you're actually downloading this data set. What do you think you will find in iris, given your experiences with Deliverable 3 so far? If you were to say print space iris, what would you get back?
3D matrix.
A 3D matrix, and what shape would that 3D matrix have? A cube, and what would be the length of those 3 dimensions? How many rows, columns, and stacks? 4, 3, 150, possibly. You will actually have a look in this assignment. The way they actually do it is it's broken into 1 2-dimensional matrix and 1 vector. What's the length and width of that matrix?
Four by 3 by 1.
No, we're just dealing with 1 2-dimensional matrix here, and then 1 vector for the classes. One matrix for the features and another vector for the classes. What do you think the shape of the feature matrix is? You got it, right? So we've got 150 rows, and throughout this assignment, we're going to eventually stop talking about irises and petals and species, and we're going to start talking about observations. So each flower is an observation. We pick one, we have 1 item. That observation, in this case, has 4 features associated with it. So each row corresponds to an observation, and each column corresponds to a feature. What do you think the length of the vector is going to be? Should be pretty easy. Not 4. We're storing the classes for our 150 flowers. 150, right? So we've got a vector of length 150. Any element in that vector has an integer either 0, 1, or 2. There's different ways, obviously, that we could store this data, but in the case of the iris data set, that's just how it's stored. So far, so good? Okay, that's the data set. Let's talk about applying this. K nearest neighbor algorithm to it. In this case, we've got 4 features. I want you, just for the moment, to forget about feature 3 and 4, and I want you to imagine that we have a 150 by 2 matrix. So let's imagine that they only measured 2 features of that flower rather than 4. The reason why I want to focus on just 2 features rather than 4 is because I can only draw in 2 dimensions. I can't draw in 4 dimensions. So let's try and visualize this data set. Along one axis, I'm going to plot the value of feature 1. And along the vertical axis, I'm going to plot the value of feature 2. So I'm going to take some data out of here and visualize it for you. This is what you're going to be doing in the first third of Deliverable 4. Let's take the first of our 150 flowers, and I'm going to draw an open circle to represent class equals 0. So this particular flower belonged to the first of the 3 iris species. It had a relatively high value of feature 1 and a relatively low value of feature 2. I'm going to take out the next flower, the second flower. This flower happened to belong to the second class. I'm going to pull out a third flower, and that one happens to belong to the third class. And I'm going to do the same for all 150 flowers. I'm not going to draw them all. Okay, that should be enough, I think, for our purposes. Okay, so let's imagine I've drawn all 150 flowers here. How does the k-nearest neighbors algorithm work? Well, now that we have this data set, we imagine that some other botanists or some other non-experts go out into the field, literally, and pick a new flower. All they know is that that flower is an iris. They know the genus. They don't know what species it belongs to. They measure, they're told how to measure the two features. They measure the length of the petal and the width of the petal, and that particular unknown flower ends up at this point in the space. Which species do you think this flower belongs to? Which of the three species does it belong to? You're running a machine learning algorithm in your head right now. Let's see how good it is. C2, why C2? Here's 1, 2, 3, 4 instances of C2, right? Most people, if you show them the problem in this way, the first algorithm they come up with is something that's very close to k-nearest neighbors, right? Your intuition is that you're going to look at other flowers that are close to the mystery flower in feature space, right? Flowers that had similarly long and similarly wide petals, right? There's many more C2s that are closer to our mystery flower than there are X flowers, and that's pretty much how k-nearest neighbors works. We take our two features in this case, and the only parameter you need to supply to k-nearest neighbors when you get it running is how many neighbors are you going to look at. Let's say for a moment we set k equal to 5. We're going to start at our mystery flower and we're going to find the k nearest neighbors, which in this case is 5. So that's this one, this one, this one, this one, and this one. And as you can see in this case, the majority class among those 5 neighbors is C2. So we're going to predict that this flower belongs to the third species. We don't know unless we go and actually ask an expert, but we can use this data set to make predictions. So far, so good? Okay, so a lot of new terminology here. Observations on the rows, features on the columns, classes, and predictions. Okay, I just walked you through the intuition of k-nearest neighbors. You're going to be coding it up in Python. We just talked about 2 phases of a machine learning algorithm, the training and the testing. So the training is collecting all of this data and using it to set our machine learning algorithm. Testing is when we then take we take new observations that didn't exist in the training data, that have unknown classes or categories. We provide that test data to our algorithm and we see how well it does at predicting the actual class. So let's say our mystery flower here actually did belong to the third species. Then our machine learning algorithm is it's batting 1,000, right? 1 out of 1 so far. What about this? What about a mystery flower right here? If k is equal to 5, what do we predict now for this one? A little hard to tell which ones are the closest ones, right? Let's see. Here's our mystery flower right here. This one is definitely close. This one is close. This one is close. This one is close, and this one is close. Still, there are 3 instances from C2 and only 2 instances from C0. So we'll predict again that this flower actually belongs to class 2. Let's say in this case we were wrong. It actually belongs to C1. So now we're not batting 1,000 anymore. We've had 2 observations and we've got 1 out of 2 predictions correct, right? So we're at 50% prediction accuracy. Towards the end of deliverable 4, you're going to be looking at the end just at percentages. So you know how well your machine learning algorithm is doing based on that percentage accuracy. How close to 100% can you get? Okay, let me remove my two mystery flowers here. What happens if k is very large? How would our machine learning algorithm behave in this case? How well do you think it would do? Better? Can we be more specific?
I think it would do a lot worse.
Why?
Because it would just take into account a massive area, and whichever one has the most data points in total, it'll always predict.
Absolutely, right? No matter where our mystery flower finds here, we're casting a huge net, right? We're looking for 100 nearest neighbors. I haven't drawn 100, so it would take all of these. So it's probably going to do pretty poor because it's always going to predict the majority class, whatever species of the 3 is most common in that set of 150 flowers. So again, let's be a little bit more specific. What would KNN predict given this data in this case? What would it always predict? C2, right? There's 4 C2s, that's in the majority. Every flower you give it, it'll say that's C2, that's C2, that's C2. As you can imagine, it's probably not going to do very well, right? Okay, so maybe we don't want a very large K. What happens if we have a very, very small K? How do you think KNN will do in this case? Also pretty poorly. Why?
Because it's only taking into account like the closest one. So if there's like 4 that are like very close, but there's that one that's just like right next to it, it won't take into account 4.
Exactly, right? So in this case, the prediction, any prediction is going to rely on a very small piece of data, right? Just your nearest neighbor. So it's easy for errors to creep in. So here are 4 C2s. Let's put our mystery flower here. It's slightly closer to C. Slightly closer to C0. So with k equals 1, it'll predict C0. But there are also a whole bunch of C2s nearby, right? So that prediction is probably not going to be very reliable. So now hopefully you can see that there is a black art to machine learning, which is, before you start, figuring out how to set the parameters that influence how the machine learning algorithm is going to operate. So what should k actually be? It's hard to say a priori for any given data set. So a lot of what you're going to be doing towards the end of deliverable 4 is fidgeting with k to find something that's good in the middle that will bump up the prediction accuracy. How many of the unknown mystery flowers does it get right?
Instead of like setting an amount, is it possible to set an area so that you wouldn't have to or it wouldn't all depend on how many there are rather than how many in this certain area?
Okay, so maybe instead of just looking at a fixed number of neighbors, no matter how close or how far away they are, we could look at an area instead. That's a pretty good intuition. What kind of area might you want to specify? Did you have an idea?
I was going to say something else. I was going to say a percentage of the whole data set you could use, because like you said, k equals 100 wouldn't work for 150, but if there's 1,000 points, then it might be a little more realistic. So
we could try that, right? We could say, all right, let's set k equal to 10% of the entire data set. Is 10% good? 5%, 50%, 20%. So we still got this issue about finding the sweet spot, but at least it's now robust to the size of the data set. So the entire field of machine learning, which has been going for about 40 years, these are the kinds of questions they ask, right? KNN, as you can probably imagine by now, is incredibly intuitive. It takes about 5 lines of code to write it, but it's riddled with problems. It's known as a weak learner. It's very intuitive, but not very good. At the other end of the scale is deep learning, which is the current state-of-the-art best machine learning algorithm that's out there. You probably have a deep learning algorithm running on your phone, probably right now. Autonomous cars, all that sort of stuff is being set up with deep learning. Deep learning is much less intuitive, much more complex, but it gets a way higher prediction accuracy than k-nearest neighbors. So we're going to start you off with KNN. If you want, you can replace KNN with something else from scikit-learn. Scikit-learn comes with hundreds of machine learning algorithms that you can use. You're not going to be assessed in this class on how accurate the predictions of your system are. All that we ask is that your predictions are better than 50%, better than flipping a coin. If you can do better than 50% by the end of deliverable 4, you're in good shape. In a machine learning class, you would be assessed on how well your learner was predicting. For this class, we just want a pretty good one that's able to sort of figure out what you're signing. Okay, so what is the deliverable for deliverable 4? Again, you're not going to be handing in code. You're going to be submitting, in this case, not video, but screenshots. And we've already talked a little bit about visual design. I've tried to create a visualization here where myself or the TA can very quickly tell by looking at this whether your system is making good predictions or not. So one of the first pictures you're going to make is something not unlike this. You'll see that we have 2 axes here. These do correspond to the first 2 features of the iris data set. There are not 150 flowers here. There are 75. So we take the original data set of 150 flowers, we pull out 75, and that becomes the training data that we looked at here. We take the second set of 75 flowers, we hide the class, and we then you're going to run your KNN on that second set of 75 and see how well your KNN does at predicting the classes of those 75 mystery flowers from the 75 flowers that you already have. So far, so good? Okay, so you understand what the positions are these 75 flowers. What's the color represent here?
The different types of flowers.
The different types of flowers, right? So for our purposes, I don't know much about irises. We're going to have red irises, green irises, and blue irises. The second visualization now, I've added the 75 mystery flowers. So the 75 training flowers, you can see they've got a black line around them. The other 75 dots have colored lines around them. What do you think the color of the edge of the lines around the circles represents? So the color of the dot itself represents that flower's actual class, which of the 3 species it belongs to. What do you think the color of the edge represents? The guess, the prediction, right? So the face color, the center color of the circle is what the flower actually is, or at least determined by an expert botanist. The edge, the color of the edge, is the prediction produced by KNN. So again, the points that have black edges, that's the training data, right? We're not predicting the classes of the training points. We're predicting, or a KNN algorithm is predicting the colors, predicting the colored edges here. How did KNN do in this case? Can you tell just by looking at the visualization how well KNN is doing? Let me see if I can zoom in for you. At predicting those 75 mystery flowers. Better than 50%? That sounds about right. How do you know? You're looking at it? Okay. What aspect of this visualization is telling you that KNN is doing better than 50%?
The amount of dots that are solid and don't have an outline.
Exactly. So the points that are solid don't have an outline, or at least have an outline that's the same color as the center. What does that mean? They guess right. If there's a dot here, like, for example, this one, this particular flower actually is a blue iris but the KNN is predicting that it's a green iris, right? Its prediction is wrong. So at a glance, in this case, we can see how well KNN is doing in this case. And again, as I said, it doesn't matter really how well it's doing as long as it's doing better than 50%. So far, so good? Okay. So these two screenshots will help you as you're going through deliverable 4 to make sure everything's working. Your 75 flowers should end up at these particular positions and with these particular colors, so you should get this one perfectly right. Once you add on KNN to your training set, you should get this picture. This is for features just F1 and F2. What you're going to be handing in is just a single screenshot, and that single screenshot is not using F1 and F2, but using just F2 and F3. So you're going to be submitting to us a picture of colored dots. The positions of those dots are going to be different because the axes are no longer going to be F1 and F2. They're going to be F2 and F3. And we're going to look to see, is it doing the same thing as our KNN algorithm when supplied with features 2 and 3. We're all working from exactly the same data set, the iris data set. We're all going to use exactly the same KNN algorithm with K set to, I think actually it's set to 15 in deliverable 4. So we'll be able to see whether your KNN algorithm is working correctly. Why am I not asking you to submit a visualization of KNN working with all 4 features? Because you'd have to draw a 4-dimensional picture, right? Even if you could, we wouldn't be able to interpret it. So we're going to stick with 2. We're hobbling KNN because we're hiding 2 of the features from it, right? So we're going to use visualizations for now, just so you build up an intuition for how KNN works and whether your KNN algorithm is working well or not. Then, when you finish deliverable 4, you're going to throw away the visualizations and run KNN with all 4 features. And what do you think will happen? It'll probably work a lot better. So now you're going to be just looking at percentages. So with 2 of the features, I think you get about 80% prediction accuracy. When you give it the other 2 features, it'll jump up to something else. What happens if one of these features was just random numbers? How do you think KNN would digest a confounding feature, something that has no real data in it? What would happen to the prediction accuracy? It
would drop. I mean, that would be useless data, wouldn't it?
Exactly. So in deliverable 5, going forward, you're going to have to be vigilant and look for these kinds of things. Are you giving the KNN algorithm data that it can actually use to make successful predictions about, is the user actually signing 0, 1, 2, 3, and so on, or not? And how do you know? So for now, you'll be able to rely on visualizations. As we go forward, the only thing you're going to be able to do is change this matrix and this vector and look at the prediction accuracy. Does it go up or go down? Okay, any questions about KNN? All right, I will just give you a teaser trailer for deliverable 5, which is coming up. As I mentioned, deliverable 4, you can set aside leap motion. You don't need it. We're just going to run KNN on the iris data. In deliverable 5, you're going to be bringing back data from leap motion. What do you think you're going to supply to KNN in deliverable 5? You're going to be supplying data from the hand, but what data? Sorry? The points at each end of the bone, right? So in deliverable 3, you're creating a 3D matrix, a 5 by 4 by 6 matrix. KNN doesn't take 3D matrices. It needs observations on rows and features on columns. So in deliverable 5, you're going to have to take your 3D matrix and turn it into a 2D matrix that KNN can digest. How do you think you're going to do that? What will go on the rows and columns in that case? what are the observations? So if we're going to try and train KNN to recognize is someone signing 3 or 6 or 9, what's going to go on a single row in that matrix?
Be like fingers and bones.
Fingers and bones and,
Hands.
well, we've got the 5 fingers, 4 bones. How many features? How many features in one frame of data from Leap Motion? What is KNN going to need to have to be able to predict, is this 0, is this 6, is this none of the above?
Like 120.
120, right? We have to take all 120 3D coordinates, 5 times 4 times 6, line them all up, so you're going to have 120 columns, right? 120 features, and the output is still going to be a single integer. What is the class that is going to be associated with those 120 features? 0 through 9, right? This is going to be KNN's guess. I think they signed 0. Or the user is going to say, I'm signing 0. Learn that this is 0. I'm signing 1. Learn that this is 1. This is 2. This is 3. You're going to teach KNN what 0 through 9 in American Sign Language is. It doesn't know, right? Okay, so we're going to have 120 columns, and we know what's going in our class vector. What's going on the rows? What's contained in a single row? Just, what's that? An observation, right? In this case, it's observation is equal to 1 frame from the Leap Motion device, right? 1 capture is 1 observation. So if you've finished deliverable 2, so if I'm signing 0 and I bring my secondary hand in to record, it's going to start spitting out data files, and these are all going to get a class of 0. So I'm signing 0. I'm teaching KNN that this is 0. Let's say that when I bring my secondary hand in and out of the recording frame, we grab 119 frames of data. You save out 119 data files. You're going to get 119 rows with 120 columns. And those the first 119 entries in the categorization vector are going to be 0. Now I sign 1, and I start recording, and I spit out 327 frames, 327 instances, or 327 rows of class 1, right? So you're going to generate in Deliverable 5 a huge training matrix which contains a whole bunch of 0s, a whole bunch of 1s, a whole bunch of 2s, and so on, right? Run KNN. KNN doesn't care whether these are flowers or frames from Leap Motion. All it knows is features, observations, and categorization and classes. Now, once you've collected that data, you turn everything off, you turn it back on. Instead of loading in the data, you're just loading in your KNN algorithm. Some other user comes along and they do this over the Leap Motion device. And we're going to see whether your KNN algorithm correctly predicts the current user is signing the digit 1. Make sense? Okay, that's Deliverable 4 and a teaser trailer for Deliverable 5. Any questions about that? Okay, so we've got a grand total of 5 minutes left. So let's go back to actual lecture. We've been talking about design as it relates to HCI. We've been talking about the fact that you're going to need to do a lot of user testing in HCI. You're going to get a taste of this next week. So we got to, where did we get to? We got this far last time. One of the things that's unique about HCI compared to software engineering is this fact that we're doing all of this user testing. We're not just trying to prove that our functional requirements are correct. The software correctly predicts hand gestures and so on. Those are functional requirements. They have to do with what functions exactly your software should instantiate. but how these additional non-functional requirements that are kind of global and kind of vague aspects of the software. Is it accessible? Is it usable? Is it acceptable? Is it engaging? And so on. We ended last time by talking about this issue of acceptability. Let's move on to the fourth and most subjective aspect of interactive systems design, which is engagement, right? So usually in HCI, you're trying to create an interface that's engaging to the user. It might work just as well as somebody else's, but your user prefers to use your interface over your competitor's interface because they like it. But that's kind of a vague thing. How would you actually measure engagement? We could measure how long someone agrees to use our software. There are other things we could do, right? This is the most subjective of all the four non-functional requirements we've looked at. Well, what does it feel like to be engaged with a good book, a good movie, a good conversation, right? If you ask someone, the language they tend to use is usually very similar. It has these metaphors about being drawn in, time seemed to fly by. When I stopped, I had no idea how much time had gone by. This particular psychological phenomenon has actually been studied quite a bit in psychology, and in particular by Csikszentmihalyi. You will not be asked to pronounce his name on the quiz tonight, I promise. He wrote a fantastic book on this called Flow. If you're interested in this topic, it's a great book to read. He interviews people from all walks of life who are at the top of their game, and they all describe this sort of optimal experience where time seems to kind of slow down. They have plenty of time to catch the ball or do whatever it is that they're doing. You've all probably had the same experience with a good book, a good movie, and perhaps a good video game or a good piece of software, right? So this last one is really hard to measure quantitatively. This is usually where a good survey comes in handy, right? What kind of language does your user use when they describe that? Okay, other things to look for in terms of engagement. When someone uses a piece of software, there's lots of other things going on. Some of them have to do with identity. Does your platform kind of mesh with your sense of self? Great example of this was the Mac ads from a few years ago. People remember these? I'm a Mac, I'm a PC. Sorry? More than a few years ago, right? I'm showing my age here, right? More than a few years ago. Who wants to be a PC, right? Look at this poor guy, right? Better to be young and wearing a t-shirt and very laid back, right? That's what Mac is all about, right? The advertising campaign was saying, this machine is a reflection of your identity, right? Very, very clever. All right. Whatever interface that you're designing, does it have a narrative, right? Does it have a flow? If you're trying to teach somebody ASL and they say, God, I don't know where I am. Am I at the beginning? Am I going back? Am I going forward? What does it actually mean to navigate? Does your user have a sense of where they sit in the landscape of your system, right? Are they actually making progress? How do they know? This aspect of immersion, right? Sometimes this is literally immersion if we start talking about augmented reality and mixed reality and Google Glass or Pokemon Go, right? The virtual world, or you are actually being immersed in this illusion that's being cast. Okay, I think we're out of time. That's the end of lecture 4. So again, please come and join us at the Flash Mob in Farrell Hall this afternoon. Enjoy Zemo next week. I will be away. I will see you on Monday the 26th when we'll start on lecture 5. You have a quiz due tonight. Have a good weekend.